Article 210.9 of the National Electrical Code addresses the use of separately derived systems. Specifically, Article 210.9 states that separately derived systems shall not be used to supply the same load or premises served by another system. A boost transformer, when configured to increase voltage, can create what is technically considered a separately derived system. In a scenario described, a boost transformer is used to increase the voltage from 208 volts to 240 volts to supply a sewer pump motor. Simultaneously, one output leg of the boost transformer is connected or jumpered to the control panel of the sewer pump, while the neutral connection for the control panel is derived from the building's main power panel. This configuration is a violation of Article 210.9 because the boost transformer creates a separately derived system that feeds the same load, which is the sewer pump motor, while another part of its system, the control panel, is fed from the original building power supply. The critical aspect to understand here is the definition and implications of a separately derived system. A separately derived system, as defined by the NEC, is an electrical source other than a service that has no direct electrical connection to the server's conductors. In simpler terms, it's a new source of power created from an existing one, but electrically isolated from it. Common examples include generators, transformers, and even some types of inverters. The purpose of Article 210.9 is to prevent potentially dangerous circulating currents and voltage imbalances that can occur when multiple power sources are interconnected to supply the same load without proper coordination and isolation. In the given scenario, the boost transformer is intended to provide the necessary 240 volts for the sewer pump motor, presumably because the building's main power supply only offers 208 volts. However, by also connecting a leg of the boosted voltage to the control panel and simultaneously using the building's neutral for the control panel, you are effectively creating two different electrical pathways supplying the same equipment. This can lead to several problems. Firstly, it can cause circulating currents between the two power sources, the boost transformer and the building's main panel. These circulating currents can overload conductors, cause overheating, and potentially damage equipment. Secondly, the voltage difference between the two sources can create voltage imbalances, which can negatively impact the performance and lifespan of the sewer pump motor and its control panel. Thirdly, it introduces potential ground fault issues, making it harder for overcurrent protection devices to operate correctly. To rectify this situation and comply with the NEC, there are several possible solutions. Firstly, if the sewer pump motor requires 240 volts, the ideal solution would be to provide a dedicated 240 volt circuit directly from the building's main power panel, if available. This eliminates the need for the boost transformer altogether and ensures that the entire system is powered from a single, properly grounded source. Secondly, if a 240 volt supply is not available from the main panel, you could consider using a different type of transformer that is specifically designed to provide an isolated 240 volt supply for the entire sewer pump system, including the motor and the control panel. This transformer would need to be installed in a manner that creates a true separately derived system, meaning that the neutral of the transformer's secondary winding would need to be bonded to ground at the transformer, and all wiring for the sewer pump system would need to originate from this transformer. Thirdly, another approach could involve using an autotransformer instead of a boost transformer. Autotransformers do not provide electrical isolation between the primary and secondary windings. They can be used to step up or step down voltage, but they do not create a separately derived system. However, careful consideration needs to be given to the grounding and bonding requirements when using an autotransformer to ensure safety and compliance with the NEC. It is also crucial to ensure that the overcurrent protection devices, such as circuit breakers or fuses, are properly sized and installed to protect the entire system, including the transformer, the motor, and the control panel. Furthermore, all wiring and connections must be done in accordance with the NEC and local electrical codes, using approved materials and methods. In addition to Article 210.9, other relevant articles of the NEC may also apply, depending on the specific installation. These may include articles related to grounding and bonding, overcurrent protection, wiring methods, and motor circuits. It is always recommended to consult with a qualified electrician or electrical engineer to ensure that any electrical installation is safe, compliant, and meets the specific requirements of the application. They can assess the situation, determine the best solution, and perform the work in accordance with all applicable codes and standards. In summary, using a boost transformer in the manner described to supply a sewer pump motor and its control panel is a violation of Article 210.9 of the NEC. This article prohibits the use of separately derived systems to supply the same load as another system. To correct this violation, you should either provide a dedicated 240-volt circuit from the main panel, use an isolated transformer to create a true separately derived system for the entire sewer pump system, or consult with a qualified electrician to determine the most appropriate and compliant solution. This explanation is purely for informational purposes and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician or electrical engineer before performing any electrical work. Remember that electrical work can be dangerous and should only be performed by qualified individuals who have the necessary training and experience. It's also worth noting that the NEC is updated regularly, so it's important to stay up to date with the latest edition and any local amendments. This ensures that your electrical installations are always safe and compliant. Furthermore, local jurisdictions may have their own electrical codes and regulations that are more stringent than the NEC, so it's important to be aware of and comply with these requirements as well. The NEC provides a comprehensive set of guidelines for electrical installations, but it's not a substitute for sound engineering judgment and professional expertise. When in doubt, always consult with a qualified professional. The NEC also addresses the grounding and bonding of electrical systems. Proper grounding and bonding are essential for safety and for ensuring that overcurrent protection devices operate correctly. The grounding system provides a low impedance path for fault current to flow back to the source, which allows the overcurrent protection device to trip and de-energize the circuit. The bonding system ensures that all metallic parts of the electrical system are at the same potential, which reduces the risk of electric shock. Article 250 of the NEC covers grounding and bonding requirements in detail. It specifies the types of grounding electrodes that are permitted, the size of grounding conductors, and the methods for bonding metallic parts of the electrical system. It's important to follow these requirements carefully to ensure that the electrical system is properly grounded and bonded. In addition to grounding and bonding, the NEC also addresses overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. An overload occurs when the current in a circuit exceeds the ampacity of the conductors. A short circuit occurs when there is a low resistance path between two conductors that are normally at different potentials. Overcurrent protection devices are designed to interrupt the flow of current in a circuit when an overload or short circuit occurs. This prevents the conductors from overheating and potentially causing a fire. Article 240 of the NEC covers overcurrent protection requirements in detail. It specifies the types of overcurrent protection devices that are permitted, the size of overcurrent protection devices, and the location of overcurrent protection devices. It's important to follow these requirements carefully to ensure that the electrical circuits are properly protected. The NEC also addresses wiring methods. Wiring methods refer to the way in which electrical conductors are installed and supported. The NEC specifies the types of wiring methods that are permitted, the size of conductors, and the methods for supporting conductors. Common types of wiring methods include rigid metal conduit, electrical metallic tubing, flexible metal conduit, and cable. The choice of wiring method depends on the application and the environment. For example, rigid metal conduit is often used in areas where the wiring is exposed to physical damage. Cable is often used in residential applications. Article 300 of the NEC covers wiring methods in general. Articles 310 through 398 cover specific wiring methods in detail. It's important to follow these requirements carefully to ensure that the wiring is installed safely and correctly. Finally, the NEC also addresses motor circuits. Motor circuits are electrical circuits that supply power to motors. Motors are used in a wide variety of applications, including pumps, fans, and compressors. Motor circuits have special requirements because motors can draw a large amount of current when they start up. The NEC specifies the size of conductors, overcurrent protection devices, and disconnecting means for motor circuits. It also specifies the requirements for motor control circuits. Article 430 of the NEC covers motor circuits in detail. It's important to follow these requirements carefully to ensure that the motor circuit is properly protected and that the motor operates safely and reliably. In summary, the NEC is a comprehensive set of guidelines for electrical installations. It covers a wide range of topics, including grounding and bonding, overcurrent protection, wiring methods, and motor circuits. It's important to follow the NEC carefully to ensure that electrical installations are safe, compliant, and meet the specific requirements of the application. Remember to always consult with a qualified electrician or electrical engineer before performing any electrical work. Let's consider some additional scenarios related to boost transformers and separately derived systems to further illustrate the principles and potential code violations. Scenario 1 involves a situation where a boost transformer is used to increase the voltage for a specific piece of equipment, but the neutral connection for that equipment is inadvertently shared with another circuit that is not part of the separately derived system. In this case, even if the boost transformer itself is properly grounded and bonded, the shared neutral connection can create a path for circulating currents and voltage imbalances, leading to a violation of Article 210.9 and potentially causing equipment damage or safety hazards. The key here is to ensure that any equipment powered by a separately derived system has its own dedicated neutral conductor that is isolated from all other circuits. Scenario 2 involves a situation where multiple boost transformers are used in parallel to increase the voltage for a large load. While it may seem like a straightforward approach to simply connect multiple transformers together to achieve the desired voltage and current capacity, this can create a complex electrical system with multiple potential points of failure and code violations. The NEC requires that transformers connected in parallel be properly coordinated and protected to prevent circulating currents and ensure that the load is evenly distributed among the transformers. Failure to do so can result in transformer overheating, voltage imbalances, and potential safety hazards. Scenario 3 involves a situation where a boost transformer is used to increase the voltage for temporary power application, such as a construction site or a special event. In these cases, it's especially important to ensure that the boost transformer is properly grounded and bonded, and that all wiring and connections are done in accordance with the NEC and local electrical codes. Temporary power applications often involve harsh environments and increased risks of electrical shock or fire, so extra caution is required. Scenario 4 involves the use of a boost transformer in a residential setting. While boost transformers are more commonly used in commercial and industrial applications, they may sometimes be used in residential settings to power specific appliances or equipment that require a higher voltage than the available supply. In these cases, it's crucial to ensure that the boost transformer is properly installed and protected, and that all wiring and connections are done in accordance with the NEC and local electrical codes. Residential electrical systems are often more susceptible to overloads and short circuits, so extra care is needed to ensure safety. Scenario 5 involves the use of a boost transformer in conjunction with a generator. Generators are often used as backup power sources in case of a power outage. If a boost transformer is used to increase the voltage from the generator to match the voltage of the building's electrical system, it's important to ensure that the transfer switch is properly configured to prevent backfeeding and to isolate the generator from the utility grid when it is in operation. Backfeeding can create a dangerous situation for utility workers and can also damage the generator and the building's electrical system. In all of these scenarios, the key takeaway is that boost transformers, when used to create separately derived systems, require careful planning, installation, and coordination to ensure safety and compliance with the NEC. It's always recommended to consult with a qualified electrician or electrical engineer before installing or modifying any electrical system that involves boost transformers or separately derived systems. They can assess the situation, determine the best solution, and perform the work in accordance with all applicable codes and standards. Remember that electrical work can be dangerous and should only be performed by qualified individuals who have the necessary training and experience. The information provided here is for general informational purposes only and should not be considered a substitute for professional electrical advice.